In the last part about oscillation, simple harmonic motion, we will talk about damped and forced oscillations and resonance. When you look, for example, at a motorbike, there are many different parts where damping is taking place. If there would be no damping, you would be jumping all over and you would have almost no control when you are driving your motorbike in a corner at high speed. The same is for cars. So damping is a vital part of a motorbike and a car in order to keep the forces under control and to avoid actually skidding. Damping. Yeah, so far we have considered SHM as there is no energy that is leaving the surrounding. However, in reality, even with a bungee jump, you might have done it before, you will see it at a certain moment. There is no oscillation anymore. That means there is loss in a form of heat, friction, and sound. Yep. Yeah, and at the end all the energy has been dissipated. That means that the oscillation stops. We have different categories, or we can divide damping in different ways. We have underdamping, critical damping, overdamping. When we look at underdamping, that means there is a small resistive force. This causes a gradual exponential drop in the amplitude. Yeah, remember I showed you the video wherein I connected a spring with a mass which was connected to a force meter, and we could see clearly the damping if there was friction. Underdamping. That means that the period of the oscillation increases with a degree of damping. Okay. Critical damping is that the resistance returns to the system to equilibrium as quickly as possible without any oscillation, and this is what we call critical damping. You don't see any, almost no, you don't see harmonic motion at all. Yeah, and this is a particular case of damping. Overdamping is the resistance is so great that no oscillation will occur at all, just the same as in critical damping. The return to equilibrium is slower than in the case of critical damping. We do a little bit more than the curriculum in the A level, but it doesn't matter. We have the red line is normal SHM, then we have underdamping, we have the critical damping that goes directly to the equilibrium, and we have overdamping. It takes longer to go to the equilibrium, or to, let's say, 0% of oscillation. Okay, what are the forces involved in damping? It normally involves the application of a periodic force, and the oscillator eventually adopts the force frequency. Now, what do we mean by a natural frequency of an object? That means it is allowed to move freely. Oscillation tend to occur at a natural frequency, which we denote as f0. Now, when do we have are we talking about a natural frequency? For example, if you have been washing your clothes and the tumble is rotating very fast, there is at a certain moment where there's a kind of vibration that is much harder And you hear that, you hear the sound of the washing machine, and this is actually that occurs at a natural frequency. So each object has its own natural frequencies, even our bodies, even bonds between atoms, they have a natural frequency. Think about the microwave and how it is heating up water. Okay, we also have mismatching forces like this. Yeah, this is when the driving frequency is different from its natural frequency. But we will have some oscillation, but a little bit. So we come now to the resonance. I've shown you this video of this bridge in the 1920s, where there was a hard wind on the bridge. This bridge already had some trouble, but the wind was blowing onto the construction, and the construction was about to vibrate, and as it happened, it vibrated with its normal frequency. And when it vibrates with its natural frequency, that means it's like pushing at the same time at the right moment, and the amplitude gets bigger and bigger. Oh dear. Here we can see the video. And we see that the bridge vibrates more and more until it has reached a breaking point. And the forces are so big on the bridge that it will fall apart. And you see the bridge is about to break. Yep. It's still amazing that it still is holding up with all these vibrations. So clearly here a construction error is made. Oh, he's saving the board. Right on time. Let's wait for the moment until the bridge collapses. And now we get a total collapse. There it goes. Oh, Okay, resonance a little bit. What is a resonance? Well, resonance, to be able to qualitatively explain how a system behaves at resonance, and on the other side of resonance in terms of amplitude and phase, to look at some real world examples of resonance. Simple definition is that the resonance is a tendency of a system to oscillate with a larger amplitude at some frequency than at others. And this is happening with the natural frequency of the object, okay? Or we call it the resonant frequency. We have, in example, some electrical resonances, and we see that the amplitude increases by a lot. Not going to show this video, I'm not going to show this applet, but let's have. When you are swinging, you remember you were a child, you were on the swings, then what was the moment that you could go harder and harder? When you give exactly a force when you are at the top and push your weight downwards, yeah? So it's like a periodic force that you are exerting on the swing, yeah? And you get actually a forced oscillation, and if your timing is correct, the pushes takes the swing higher and higher until, if you're not carefully, you could break the swing. Okay, effect of some applied frequencies on the amplitude. When we look, applied frequency is 0, then the amplitude is 0 and the phase difference is 0. If we have a resonant frequency, the amplitude increases more and more, and the phase difference increases from 0 towards pi over 2 radians, or 180 degrees. At the resonance frequency, natural frequency, we get an amplitude that is significant maximum. And this happens when there's a phase difference of exactly pi over 280 degrees. The resonance frequency, when it's bigger, decreases more and more the amplitude and increases from pi to towards pi. So it gets the resonance gets less and less. So frequency, the amplitude increases by a lot when when we have an applied frequency at the right moment. Okay, lightly damped. The applied periodic force is exactly in phase with the velocity of the system. The maximum amplitude is limited by the damping. We can discuss this bit. I think this is more or less the end of this slideshow. Yeah. Obviously, when buildings are not corrected in a good way, or when there is no damping, then buildings can collapse very easily in an earthquake. Yeah. Some other examples are microwave cooking, wherein we actually have a certain frequency of the microwave that actually vibrates the bonds between the hydrogen and the oxygen in water molecule. In this case, it is 2.45 gigahertz. Some other examples are timekeeping. Did you know those old watches? Well, not so old. Yeah, these digital watches, they contain a quartz crystal, and the quartz crystals oscillates with a very typical frequency, and it's so perfect that you only have to calibrate it and connect it to a digital board to find the time. Okay, some keywords. Natural frequency. Frequency which A system oscillates without an external periodic force being applied. Periodic force, a force with a regular changing amplitude and definite time period. We have forced oscillations in which the system is exposed to an external periodic force. We have resonance for a lightly damped system. The amplitude of the oscillation tends to a maximum when the frequency of an applied periodic force is the same as the natural frequency of the system. Okay, this is the end of unit oscillations, and then the next time this weekend I will add a new unit.